Great to be here again, and great to speak about this work, which is joined with Benoit Daguerre. But it also relates a lot to previous work with Thierry Boudinot, I'll explain. And it also involves, as I'll explain, in an important way, a new correlation inequality for Ising models due to Ding Song Sun, and I'll also explain. So there's two models in the title, and I'll discuss both of these a little bit, but let me start with the Ising case where the statement is a little bit simpler. So we look at an Ising model, and the case we're interested in is d dimensions, and we can and what we obtain is quite general, but so let me first start with the definition. So I'm using this notation, expectation mu beta h for the Ising model with a temperature, inverse temperature beta and external field h. The external field can be anything. So this expectation is the sum of all spin configurations, sigma and plus minus 1 to the lambda. Lambda is finite. E to the minus of beta over 2, sigma and sigma. E to the sigma, the external field, right? And I will normalize the model by normalizing this matrix A as follows. I assume that A is positive definite. We can always impose that by possibly adding a diagonal to the matrix A. Doesn't change anything, doesn't change the model. I'm assuming that the largest eigenvalue of A is less than 1. So this is the operator norm. So that's also basically corresponds to fixing the temperature in some way. But then it will be important that A has negative off-diagonal entries, so that the model is ferromagnetic. And so the Log-Sobolev inequality for the Ising model is the best constant. The Log-Sobolev constant is the best constant, which I denote by gamma in the Log-Sobolev inequality. And the Log-Sobolev inequality reads as follows. I'm looking at the relative entropy of F. So F is going to be non-negative, and I'm thinking of F as a density with respect to this measure, say. But it's a non-negative function on R to the lambda. And the relative entropy is then, well, expectation beta h of phi of F minus, well, if F has expectation 1, then the second term can be omitted. Where this function phi is x log x. So that's the relative entropy. And the Log-Sobolev constant is the inequality that bounds the relative entropy of F in terms of 2 over the Log-Sobolev constant gamma times the Dirichlet form of the square root of F. This is sometimes called the Fisher information, or I guess it goes under other names, which I can't remember. But anyway, it's defined like this. We sum over all vertices lambda, and then we take the square, the expectation of the square of the gradient of F, where gradient means I'm flipping the sign of the spin at the side x. So taking a spin configuration sigma, which is a plus minus 1 to the lambda, and then I'm sigma x is the configuration where the sign at the side x is changed. So the best constant in this inequality is the Log-Sobolev constant. This is the Log-Sobolev inequality. And its relevance is that it gives a good bound on how the, so this is a Dirichlet form. So there's a dynamics associated to it, which is the Glauber dynamics, continuous time Glauber dynamics. And the question we're interested in, how fast does it relax to the invariant measure? And the Log-Sobolev constant gives the rate in the measure of relative entropy. So if Ft, so we start with some density F, say probability density, then we can define Ft as the density evolved at time t, according to this Glauber dynamics, which is generated by this Dirichlet form, and the Log-Sobolev constant gives the rate at which this relaxes to 0. So we're interested in getting a good bound on the Log-Sobolev constant, and
now that's an upper bound in terms of Log-Sobolev constant, but I mean it isn't sharp, right? I mean you want to.
Well, it's essentially sharp. It's essentially sharp. It's essentially sharp. It's in the continuous case, it is exactly. In the continuous case, the Log-Sobolev constant is exactly the best rate and the rate entropy relaxation. In the discrete case, there's a question of how you write the Dirichlet form. So it's not. There could be better, but for the cases,
for purposes, then it is the right. It is the right answer. Yeah. It is right.
Yeah.
And the errors are the definitions, right? You call entropy the errors and the difference of this. These are the definition of the object. What do you mean by the errors?
Sorry?
Yes. This is equal? You mean
that's equal. That's a definition.
It's equal.
The arrow means definition.
Definition. And the arrow up is a consequence.
That's a consequence, exactly.
When gamma is up instead of down?
This one? Why it's up?
Yeah, you see there is gamma t and 2 over gamma, maybe it's obvious, but.
Oh, why is the exponent? Well, it's just so it's kind of like if you don't put the square roots here and you put a variance instead of the entropy here, then what you get is the spectral gap of the operator. And this is this implies also bound on the spectral gap, but it's a bit stronger. But for the purpose of this talk, you may think of them equivalent. We're not really interested in the difference. It's just what comes out naturally, and it's the strongest form, so might as well state it this way. So what we get is surprisingly simple inequality. So it's an inequality on it's a lower bound on gamma. So an upper bound on 1 over gamma, the time to equilibrate, and the bound is simply this. It looks a little bit, it may look a little bit complicated, but in fact it's much simpler than we dreamed was possible. And here Chi-S is the zero field susceptibility. So general, sum over the spin-spin correlation and external field 0.
Are you using translation variance at all?
No, not so far. If you have translation variance, you can drop the maximum.
Yeah, I was wondering whether it was necessary at all.
No, it's not necessary for anything.
What is the S dependence?
So the S is, sorry, that's a good point. It's so chi beta. So S is substitute for beta. Yeah, thank you.
No, let's see. I guess I have the same question. Chi of S. Oh, S is beta here.
Yeah, S is beta. So we're integrating the susceptibility over temperatures from 0 to T, then put in an exponential, then integrate from 0 to beta. let me illustrate this bound because it'll be clearer what it says in a second. So the first question you can ask is, well, first case you can consider is, suppose the susceptibility, so everything I'm stating here is finite volume, but you can ask that chi beta is say bounded uniformly in the volume. That's exactly basically the definition of the high temperature phase. In this case, what this bound says is that the Log-Sobolev constant is uniformly bounded below the volume. So relaxation is fast as soon as you're in the high temperature phase.
So I see.
So the chi is bounded. Gamma beta h is bounded below.
So if I'm above the critical temperature, then I'm guaranteed exponential rate of acceleration in any dimension.
Any dimension, and in fact, as you pointed out, even translation and variance, all of this doesn't really matter. I mean, as soon as the susceptibility, which is basically what always characterizes the high temperature phase, is bounded, there's exponential
convergence.
Yeah. And so this was this was actually not known for a long time. It was just proved this year for lattices in this paper of Ding Song Sun. So they use a method of dividing a lattice into blocks and devised early, I think, due to Magnelli or anyway from that period. And they verified what's called the strong spatial mixing property, which is one of the conditions that guarantees this. But it's very lattice dependent, and it sort of gets into the, you need to extract the strong spatial mixing from the fact you're in the high temperature phase, etc. So, and the advantage of this bound is it doesn't really use anything.
So fuzzy model on any graph or
yeah.
Okay.
Yeah. We also use, and I'll come back to this, correlation inequality that Ding Song Sun established. We're also using that, which they used to get the strong spatial mixing. But so this is a different, arguably simpler argument to get this very generally. But what's perhaps more interesting is that if chi beta satisfies a reasonable bound, and by reasonable I mean looking at the mean field bound, which is true due to Eisenmann's work, and dimensions 5 and higher, with some constant d, which is at least 1 in fact, and equal to 1 for the Curie-Weiss model. Then, well, you can substitute this into this bound. Well, you do the integral of 1 over beta minus beta c. You can see you get a logarithm.
Again,
and then you logarithm in the exponential. It's a polynomial. You integrate a polynomial, you get a polynomial. So, yeah. So somehow, if you have the means field bound, which is the case for Ising models on ZD and D at least 5, the inverse Log-Sobolev constant is bounded by polynomial. So the gap only closes polynomially. Most. The exponent we're getting here is it's not.
What's D?
D is the constant, the mean field bound.
Oh,
so the true bound, we don't expect there to be a D in this bound, but this is what we get under this assumption. But the point is it's polynomial.
Yeah.
In this generality, which came to us as a surprise, that it holds in this generality. You can also make a finite volume statement if you want. Say if you are in a finite box, say free boundaries for simplicity, and well then this mean field bound improves a little bit, right? You have a delta to the -2 condition, and then you could ask what happens for the Log-Sobolev constant at the infinite volume critical temperature, but in finite volume, then you get a polynomial in the size of the box bound.
So can you repeat the definition of FT?
ft, there's no f.
Not there. The entropy of ft is the.
So here. Oh, what ft is?
Yes.
Right. So so this Dirichlet form, there's a Markov process associated to it. Call it sigma t. You start with some spin configuration sigma, you evolve it. It's a continuous time Markov process for this Dirichlet form, but you can look at different Dirichlet forms. They're not always equivalent, but in, say, the finite dimensional case, they're all equivalent up to constants. You look at the spin configuration, you evolve it up to time t, and you look at the distribution at time t. If the distribution at time 0 was f naught relative to the Ising measure. So this is the distribution at time t. So it says that the distribution in relative entropy sense is close to the, so if this is 0, if this is 0, this is the invariant distribution. F is 1.
So does this last line say something about the two-phase region, or
no? So none of this. This doesn't give anything useful for the two-phase region. Basically, the issue is all these estimates, they require the zero field susceptibility, which becomes which diverges the two-phase.
Well, but I guess you put it into a finite box, and then it wouldn't diverge.
It wouldn't diverge, but it would be exponentially large. I mean, it would be large as the volume, and this bound would be exponentially large. You don't get a good bound from this. I mean, in fact, the two-phase region is not too well understood. There's some work, some recent, but in general, the optimal mixing rates are not understood, I think, at least in 3 dimensions, maybe 2 dimensions, but 3 dimensions is. It's not known as, it should be polynomial under certain boundary conditions. So if you don't put boundary conditions, it's exponentially large. It's much more subtle in the sense of boundary condition dependence, etc. So in this sense, this is much less subtle. Okay, so right, so
yeah, is it true that, I mean, this is of course a bound, so I mean, I guess one expects the power of the law there to be 2 in 5 dimensions, for example.
yeah, so this power law we always expect to be -1.
Oh, -1, okay.
In 5 dimensions, say.
Yeah.
Well, we have some ideas why we're not getting the right exponent. This exponent is bigger. It's worse than 1. I think we have some idea of what one would need to do to get to 1, but there are technical reasons we can't do it at this point, at least. I don't think you could get it under an assumption just on the susceptibility. I think you need to know more to get the right exponent.
Okay.
But
is that the same as the z exponent, or
no, I don't think it's the same. This is the z exponent, as far as I remember, it's more like local. This is sort of a global in space way to. Yeah, this is like a
local quantities necessarily.
Yeah, this is like a global in space way to measure the relaxation. The z exponent, if I remember correctly, is more like local observables, and it's not something we can I mean, that's effectively captured by this.
Like a 2-point function or something.
Yeah,
like that.
Yeah, it's like a space-time 2-point function. Yeah,
Rate of equilibration of 2-point function.
Yeah. Yeah, so we were.
That's expected to be 1. I mean,
this we did -1.
-1.
-1 is what we'd expect. But before there wasn't actually any polynomial bound, except in 2 dimensions, where there's the work of Lubetsky and Sly, who got a polynomial bound, also not the correct one. I think, I guess a similar, there's a loss. But anyway, in this case, it turned out to be also, thanks to this new correlation inequality, quite simple to get this bound.
Would there be something analogous for for, I guess, solid on solid, or in 2 dimensions, or like a villain?
That's a good point. Say discrete Gaussian would be a natural case to understand. Well, we can't currently do it. I mean,
it goes to free field again. So
yeah, it should be. But we don't currently know how to do it. Certainly thought about it, but yeah. Okay, so this is the Ising case.
So there is no H dependent in this.
Well, there's no H dependence.
So it's completely washed away.
Yeah.
Oh,
it's both a strength and it's,
yeah, that's the privilege of being a speaker.
Okay, well, as you prefer.
I mean, yeah, I think we might prefer having it off, and we probably hear you better.
I'm okay. If you can hear me fine.
I can hear you fine.
Okay. Well, then
I'm trying to.
That's okay.
Okay, I'll take it off then. Okay, so yeah, there's no H dependence, and that's both, I think, why the proof is simple, but also why
it's not optimal.
Yeah, well, why it's not optimal and why we don't get the optimal exponent, I think that doesn't have to do with the H dependence. It has to do with the fact that the susceptibility, I think, doesn't have enough information about this exponent. It's remarkable in my view still that it has enough information to get any exponent, but I don't think it has enough information to get the right exponent.
So the only polynomial cases that were known before were 2 dimensions, which
there's the 2-dimensional case of Lebesgue and Sly, and then there were various cases which sort of simpler geometry, trees, complete graphs,
and
things like
field
that.
models and all that kind of stuff. Right?
Yeah,
I mean, and so this is the first case where you can really do it for a 4-dimensional.
Well, 5-dimensional. So 4-dimensional is not quite polynomial. You also get a bound that's not horrible, but it's not quite polynomial. Right? So,
you got an extra log there.
Yeah. So in fact, this Ising model was our initial motivation for looking at this.
And one more question. I think I asked this before, but I wanted to make the point. If you knew the same bound for the XY model, or would you? No, I guess you still don't have the result. Right?
No, we don't. I mean, we don't have. So as you'll see, I mean, what we're using right now. Well, getting ahead of myself, but. We need to control a certain effective potential. And if we can control it, we would get this very generally, any model, basically. Problem is to control this, and we need strong control. And this is where this new correlation inequality is really helpful, because it allows to reduce the global and the external field control to 0 external field control, which is exactly what's given by the in terms of the susceptibility. I show this later. So it's if you could get this information in some other way, and one would hope that, say, at least in a more perturbative regime, one could maybe get this somehow. That then it would apply much more generally. The general strategy doesn't depend at all on the specific model; it's much more general. But the control, I mean, here we were lucky.
And did you tell me that Roland has a?
Yes, exactly. I was just talking to Roland Eldon yesterday, and so they have. I'll explain the methods in a bit after stating the 5-4 results. So he has quite similar methods, and I think he can get a quite similar bound. It's just looking or pairing it, but I think the bound is quite similar. It's coming from a very different direction, but it seems the methods they're not exactly the same, but they have really well anyway.
Okay.
Okay, so yeah, let me maybe briefly before I'm going to tell you a bit how the proof works, because it's actually very simple. I don't know how much time I still have. It goes by more quickly than I thought it would.
Asking all the questions.
But anyway, let me first tell you the 5-4 results, which in fact, were our original motivation. So we look at so this is the continuum 5-4 model. we regularize it by ultraviolet and infrared cutoff. So we're looking at a torus of side length L, and then we take a mesh of spacing epsilon. And in fact, all the results we're stating are in this setting, but they don't depend on epsilon and L. So in this, this is the phi-4 measure. It depends on two parameters: lambda, which is the coupling constant; mu is the mass, which can be negative. So fields are in R to the epsilon lambda, and then interaction is the phi-4 interaction. So this is like an integral over.
Sorry, why do you call this continuum if it's on a discrete?
Well, because it's uniform epsilon, you can take the limit epsilon to 0.
I see.
It's, I mean, we prefer to state everything when everything is finite, but it's a bound that's uniform, the absolute bound. So you can take the limit. Well, there's the free field term. So this Laplacian epsilon is just, defined as epsilon minus 2, some y is a neighbor of x in this epsilon mesh lattice, fy x. Then there's the phi-4 term. And then there is the mass term. So mu can be negative, if you like, but what's important is there's this counter term, which I denote by a epsilon of lambda. It's a function of lambda. So lambda is positive and mu is real. And a epsilon is the counter term. And what is a epsilon? So in 2 dimensions, you can just take Wick ordering, enough. And 3 dimensions, you need to have a second order lambda counter term with a measure. And explicitly, you can write them like this. So I write them like, well, introducing extra parameter m, but let's take it to be 1, it can be anything fixed. Then 2 dimensions, you just need to take minus 3 lambda times the Green's function at 0, 0. So this is the Green's function with the regularization epsilon. So say in 2 dimensions, this would blow up logarithmically in epsilon. In 3 dimensions, this would blow up like 1 over epsilon. And in 2 dimensions, this is enough. And in 3 dimensions, you need to add a second term, which is the L3 norm of the Green's function cubed. And this is bounded in 2 dimensions, but blows up logarithmically in 3 dimensions. So this is, and what's important is, well, it's minus, it blows up, the leading term is always negative. So it's log epsilon is order 1, 2 dimensions, and it's epsilon inverse plus C2 epsilon squared log epsilon in 3 dimensions. Okay, so this is the counter term, and this is the lattice regularized phi-4 measure, and it's known that as epsilon goes to 0, this converges on, if you interpret these fields as elements of a suitable space of generalized functions, it's known this converges to a continuum limit.
In 2 and 3 dimensions.
And 2 or 3 dimensions. Okay, so this is the phi-4 measure. So we're again interested in the dynamics of this, and dynamics is not the physical quantum dynamics, but the if you like fictitious Glauber dynamics of this measure. View this measure as
you're using the Glauber dynamics here to take the continuum limit. Is that more or less correct?
No, we don't take the continuum. I mean, you can take the continuum limit. What we're concerned with is just to get a uniform bound on the Log-Sobolev inequality independent of the cutoffs.
Okay.
So like back in the ancient days, people were talking about Log-Sobolev for 5/4 was that different from what you're doing here?
Well, yeah, I think it's different. I mean, there it was for the Gaussian measure, right?
Oh, okay, yeah.
And it was used as a tool to get, say, the bounds on the lower bounds on the Hamiltonian and in the Minkowski world.
Yeah,
I think so. It's different. I mean, we're looking at somehow the
true measure. Yeah,
the Euclidean world here.
With the weighted, with not the Gaussian measure, this is with respect to some.
Yeah, this is with respect to the non-Gaussian measure. Yeah. So, and it has, well, encodes information as in the Ising case about the relaxation of this Glauber dynamics for 5/4, which is also called the dynamical 5/4 models, which is if we have a finite epsilon, finite L, it's just a finite system of SDEs, but in the limit epsilon to 0 becomes an SPDE, and it's one of the main example of Martin Heira's theory. It's this sequence of SDEs, if you like, finite dimensional setting. It's just well, this is just the gradient of whatever is in the exponent there, and this is square root 2 times dW, and dW is what is be called a space-time white noise. In this case, it's space is discrete in space, but it's continuous in the time, where time is this extra fictitious or d+1 dimensional time. So, but concretely, this is just a Brownian motion on L2 of lambda epsilon L, where L2 is normalized with a measure that has an epsilon to the d in it. It's just a Brownian motion on this space. It's a finite dimensional space. So yes, so Heira's theory and all the developments that followed this, Gubinelli, Weber, etc. So they're concerned a lot with the fact that for pathwise, given the noise, we want to take pathwise the limit as epsilon goes to 0 of the solutions to these equations. What we're interested in is a little bit orthogonal to that. We're not really concerned with the pathwise limit of these equations. What we're interested in is the law of the solution and how it relaxes to its invariant measure. And that's, again, well, one of the ways, so it's PDE if you like. So one of the ways this is encoded is, again, in terms of the Log-Sobolev constant. And so in this case, the Dirichlet form is continuous. So it's this, I mean, there's the expectation with respect to this measure, epsilon. I added some indices. So it's just the continuous analog of what I wrote down for the Ising model. And the Log-Sobolev constant is, again, the best constant in the Log-Sobolev inequality, which in this case reads the relative entropy of F is bounded by, well, it actually is the same inequality as before. Okay.
The F to the phi x is as before, it's just the discrete.
Sorry, where?
You have the df to the phi x.
Well, this is just a continuum. This is F is a function on R to the lambda. This is a usual derivative.
Okay.
This is not a discrete derivative. Now this, well, F is so F is in R to the lambda. So it's very high dimensional, right?
I see.
So it's just the
yeah. Okay.
And in this case, what we get is, well, one of the statements we get is if you assume that the susceptibility, which in this case is defined like this, it's the sum gets replaced by an integral. Is bounded, say it's bounded by some constant, which I'm going to call chi bar, just this quantity is bounded by some chi bar. Then the conclusion is the Log-Sobolev constant, which a priori depends on everything, epsilon L and mu, is bounded below by some constant, which maybe I call gamma bar. But gamma bar depends on lambda, mu, and chi bar, but it's strictly positive. In fact, there's a formula for it, has an exponential in it, etc. But the point is, this doesn't depend on epsilon or L. So if you have a uniform bound on the susceptibility, this is bounded below, the Log-Sobolev constant bounded below. In particular, it's true in finite volume, it's always true for any coupling constants. It's uniform, if L is fixed, it's uniformly bound, this is uniformly bound in epsilon always. That's known. So in finite volume, you always have a Log-Sobolev inequality. In infinite volume, well, it's bounded exactly, that's the definition of the one phase region. And then you also have a uniform in the volume, Log-Sobolev inequality. Right, so is there anything else I should say? Yes, I think I forgot to discuss any references, but maybe that's okay. I guess I can leave it at saying that, well, there's a long history in understanding the convergence, epsilon goes to 0 of these measures and so on, and maybe I'll not attempt here to give an incomplete summary of what has been done there, but it's well understood. Quite well understood. In terms of dynamical relaxation of these SPDEs, I should mention in particular there is work by Weber and Satsoulis, who established a spectral gap in finite volume. So they work directly in the continuum limit, so not in the uniform epsilon setting, but I think it's equivalent. But so they get a spectral gap in finite volume, but no control in terms of how it depends on the volume. Mm. And this was also extended to 3 dimensions by Heira and Schönbauer. In principle, I think the result has a general part, but it involves some technical property which I don't quite understand. Maybe I shouldn't admit this in this talk, but it's a certain property which is maybe let me not go into it, but it's a certain qualitative property of these SPDEs that plays a role in these.
But again, it's finite volume, right?
It's finite volume, yeah.
So it doesn't really tell you about the gap or
right, yeah. So exactly. So what we like about this result, it extends to infinite volume, and in fact, even under the best assumption, if So if the susceptibility is not bounded above, then you can easily see that the Log-Sobolev constant is 0. So you just put a test function into the Log-Sobolev inequality, you get it. It's a simple test function, it's linear. And you see, I mean, if this is not bounded above, then there's no lower. So in that sense, this condition can't be improved. What can be improved is the bound that we get here, which especially in 3 dimensions is not going to be good near the critical temperature. I mean, even for Ising model, we actually don't know any bounds in the approach of the critical temperature, I think, in 2 and 3 dimensions. So
no polynomial bounds, or
no polynomial bound. Yeah, the exponential sort of bounds, but right. So okay, I've used more time than I thought I would just to discuss what the statements are. So I'll have to cut the discussion of the proof a little bit short. But the following principle, I think, so maybe let me focus on the Ising case for now, because this is a simpler case in some sense, because there's an additional, I mean, basically, there's some differences in the proof. I mean, there's a basic idea which is shared by the 2 proofs, but some technical differences are different. In the Ising case, there's a bit of an additional step because it's discrete. In fact, we turn it into a continuous problem. In the 5-4 case, there's more work to control the ultraviolet singularities. So in the Ising case, what we do is so these matrices A shouldn't have erased this, but was the coupling matrix, which was assumed to be positive definite in the Ising model. And we define a sequence of covariance matrices like this, where alpha is any number fixed bigger than beta. It's essentially beta. In fact, it will cancel out later on, so it doesn't really matter anything.
So I could just think of A as being the discrete Laplacian.
Yeah, A is the discrete
Laplacian.
Yeah, it's the discrete Laplacian. Except we've normalized it to be less than 1, but anyway. So then we can write the Ising measure. So this measure mu beta h, which I erased, can be written as, well, to reproduce the definition I erased. So this is the definition of the Ising measure at inverse temperature beta external field H, written in terms of the C beta inverse. Right? I mean, if I put this in, we get beta A. This term is diagonal. It doesn't matter because the spins are square 1.
So you're just moving the temperature around, really.
Well, I haven't done anything so far, but that's what we're going to be doing. Yeah. So, so I've just rewritten the original model, but now we can move the temperature as you anticipated. We can write this. Well, it's a Gaussian density. We can write it as a convolution of 2 Gaussian densities. In fact, so for any t less than beta, we can write this density like this. What does this formula say? Well, this formula is just the formula that's equivalent to the fact that if you have 2 Gaussian random variables that are independent, you add them, you again get a Gaussian random variables, and the covariance of the new Gaussian is the sum of the covariance. That's what this identity says. the point is, it allows us to somehow sneak in this extra field phi. If we put in this identity here, we have an extra integral over phi, which is we consider as a new field, and we fix or condition on if you prefer. And then we have an Ising model sigma here, where the temperature beta was replaced by T, or inverse temperature beta was replaced by T.
So you sum over, so this is equal. This is not early.
Yeah, so this is proportional. There's some constant which is independent of sigma and phi.
And you derive this, you introduce.
Well, it's just the fact if you have two Gaussian, it's the, you know this identity very well. It's the addition property of Gaussian measures.
Now I see it. I could not see it.
Yeah. That's all it is. But somehow we're using a special way to decompose the Gaussian measure. In fact, a very simple one, which just amounts to changing the temperature. This is not the best way to decompose this measure for the purpose of the renormalization group, say how we usually like to think about it, because it doesn't, well, let me not go into this, but for the purpose of what we want to do, it's very nice because it preserves the structure of an Ising model in here.
It is the F.
There's the F, yeah. So we put this identity in, we get this new integral over phi, we condition on phi, we have a new Ising model, where it remains an Ising model. There's a new external field, which is related to this phi. It's the old external field times this. And then the temperature has changed from beta, the inverse temperature has changed from beta to T.
But F?
F is just the observable.
But in the other number,
It's still there.
Still there.
let's see.
Yeah, maybe you can put it in.
I mean, I've just rewritten this part. The rest stays the same. Just rewritten this part here.
Ah, that's only this piece, that's all.
Yeah, just this piece I've rewritten. I've just put that in.
Okay.
That's for any T?
Any T less than beta. Yeah. So you can, any T less than beta means that the new Ising model has a temperature higher than the one we're looking at. And in fact, we're going to be using all T because did I erase the result? It was that I shouldn't have erased, but maybe I'll recopy it here. I mean, there was an integral. Let me recopy it here. It was something like this. So this is the bound we got for the Ising model, 0 to beta, e to the 2 integral from 0 to 2 chi s ds dt. This was the bound we're proving. So there's a not to infinity to beta. So we're going to derive, so you can see this integral will come from varying the t from 0 to beta. And if you take t equal to 0, well, then it's 1/2. This is the product measure. This is the Log-Sobolev inequality for a product measure. Okay, so we've just put in this identity. So another way to say this is we can rewrite the measure as follows. We introduce what I call the renormalized measure. I call it maybe nu t. And nu t is a measure that's basically given by the phi dependence of this, putting this in. It's a measure on phi, in the field phi. And then we have an Ising measure inside, which is, so I'm using this mu for the Ising measure at temperature T. That's what we've seen here. And the external field is the old external field. And then we have a new external field, which is plus CT inverse H, phi. So there's a phi in this measure, it comes in here. And then this is applied to f of sigma. So explicitly, if you like, so this one is the same as the Ising measure before, except different arguments, and nu t is a measure on phi with density e to the -1/2 phi c beta minus ct inverse phi minus vt of phi, where vt is the renormalized potential, and it's given by convolving. So vt of phi appearing in this equation is defined by up to a constant, which doesn't matter, always cancels out. So I'm systematically neglecting all constants that will cancel out. Okay, so this is the definition of the renormalized potential at time t. And this is the definition of the renormalized measure with, if you like, this is the Wilson action. This is the renormalized potential. And as a function of t, if you like, it satisfies the Polchinski equation. In fact, we'll use that. But I get there. So we can decompose the measure like this.
I'm just trying to figure out. So you have the phi measure. Phi measure.
So this is the phi.
You have the phi, but the phi also appears in the.
Well, this is the measure. This is the measure on phi.
Okay.
But this measure depends on phi.
Yes, I understand.
So we have a measure on phi and then a measure inside that depends on phi.
Okay, well, you're just decomposing. You're just rewriting.
I'm just putting. I really just put it this formula
in terms of two different expectations, right?
Yeah.
Corresponding to that product.
Yeah, I've just put in this identity. It gives me an extra field that's this expectation. And this is the old one, but now the temperature has changed.
Which one? So the one that I should be. Oh, I see. So the one where you sum over the sigmas, that's the first factor. Or no, you have the.
No, this is the sigma. This is the sum over sigma. So maybe I should write. So this expectation applies to the field sigma, and this is phi. So
okay. Okay.
So the inner one is an Ising model because f is a function on plus minus 1 to the lambda. It has to be an Ising model, but the outer one is continuous. And in fact, so you can, well, just differentiating the definition of VT, you see, you can use this VT to relate VT for different T's to each other in terms of convolutions by just repeating this identity, or equivalently, you can write down the differential equation for VT, which is the Polchinski equation, which is so what does this notation mean? It just means this is by definition 1/2 times the sum over x, y, and lambda. It's a very high dimensional PDE. If you like, CT dot xy. So these are the entries of that matrix C. And in fact, I'm taking the dot, means the derivative with respect to the parameter t. This is a matrix. And then taking the second derivative of b with respect to phi x and phi y, minus the derivative of respect to phi x.
How we use the whole cluster expansions, yeah. When we take the variation of the covariance.
Yeah. So anyway, this renormalized potential satisfies this beautiful Polchinski equation, and it turns out. So this is this is the ingredient that Thierry Boudinot and I developed in the context of when we were thinking about related problems for the Sine-Gordon model, which is the following condition we got. So we assume there are real constants, which I call lambda t dot, say. They're real, they can be negative. That's essential. We assume these constants are such that uniformly in phi, the Hessian of the renormalized potential VT satisfies a certain bound. And this certain bound, it may look a little bit complicated, but it's actually very simple. So we're taking the Hessian and we're taking this matrix CT dot on both sides. And then we subtract -1/2 times the second derivative of the CT dot. And we assume this is bigger than lambda dot T times CT dot, where this is the first derivative of this covariance matrix I wrote down. This is the second one. So if you have this quadratic form bound on the Hessian of dt, and I'm going to tell you in a second that while this may look intimidating right now, this will be reduced to the condition only involving the susceptibility. We just plug in explicitly what these are. I'll show you in a second. I guess my time's almost up, so maybe I can show you that and then I finish. Well, then we get a Log-Sobolev inequality for the measure nu naught, which is this measure with, I mean, we could apply it to any nu t, but we'll take it for the measure nu naught, say, formulate it like this. So this measure nu naught, this is continuous measure now, satisfies the Log-Sobolev inequality. And the constant is given by integral from 0 to beta. So this measure nu naught depends on beta, right? I didn't write this explicitly, but if you look at the definition here, there's a beta here. This -2 integral 0t lambda dot s ds, and then the whole thing integrated with respect to t. That's the Log-Sobolev constant. And you'll see it. You see how, I mean, how similar it looks to what's up there already. And then we have the expectation. So this, because the Log-Sobolev constant. Okay. Anyway, so we have this condition, and up to now, I mean, I've explained this in the case of the Ising model, how to get to this condition, but any model can get to this condition. And what we need to check is this condition. And now, okay, so maybe I'll leave this to later where this theorem comes from, but let me just mention, there's this famous theorem or this famous method of Bakri-Emery, which applies to convex models. And it uses certain decomposition in terms of like fixed semi-group, which is essentially the Glauber semi-group. But it requires a global convexity assumption. We don't want a global convexity assumption because our measures are just not convex. But we're using sort of the strategy from that method, but we run it with this with a semi-group that's given by linearizing the Polchinski equation instead. It's a time-dependent semi-group. We can run sort of the same kind of arguments with it, and the proof is more or less the same. It's not difficult. If I had like 15 more minutes, I could show you the proof, but that's how it comes out. Basically running the Bakri-Emery method, but we use the Polchinski equation to generate a good decomposition of the entropy. But anyway, at this point, it's reduced essentially to checking this condition. And well, that's actually, so let me, if I have 5 more minutes.
5 minutes or so.
5 minutes, I can do it. So VT, by definition, I guess it was written here. I'm just taking a log of this. Let me, and I want to take the second derivative of this. I'm taking the log of this, and then this minus, and then the second derivative. And so I want to, so that's the Hessian of VT. And the result is the following. It's CT inverse. That's the first term, which comes from differentiating here and here. That just gives the CT inverse. And then there's a variance term, which comes from, because we're taking a log, once we're differentiating once, we get a variance, right? And that's CT inverse. And then what appears in the middle is the covariance matrix of the Ising model, because this is an Ising model now.
With the background field.
With exactly with temperature T and a background field, which is I guess I forgot the H here. I should have put in H phi. Anyway, if we have an external field H. So it's a background field H plus CT inverse phi. And then there's another CT inverse. That's a formula for the Hessian you just get by differentiating this. And this is the point where the new correlation inequality becomes useful. Because what Ding Sun proved 21 is that for any ferromagnetic Ising model, in an arbitrary external field, that's important because this field can take positive, negative values. This is pointwise for any x and y bounded by the same thing, except you take the field to 0. We're not quite finished at this point because this is a pointwise bound. We need a bound on the largest eigenvalue because we want the quadratic form bound at the end. But also by the FKG inequality, this matrix has positive entries. So by the Perron-Frobenius theorem, the top eigenvector also has positive entries. So we can get a bound on the largest eigenvalue from a pointwise bound. So this implies, so using the pointwise bound plus the Perron-Frobenius theorem, we get this as a quadratic form is bounded by the largest eigenvalue, which is just the susceptibility. So in other words, we get this, this is bounded from below by CT inverse minus CT minus 1, well, pi T, the susceptibility, CT minus 2. Now, you need to multiply through by these CT dots, but it's, I mean, they're explicit in terms of that. Because that we don't need the Hessian itself, we need this quantity. But you just put that in and you see that this condition holds with lambda dot, just the susceptibility. And then the proof is basically done. There's a little bit you need to do to decouple these measures, but one is a product. It's easy to do that. And so this is basically the proof for the Ising model. I'm not going to write down the remaining details because my time is up. Let me just say 2 words about the phi-4 case. We have a similar condition. We're using a different decomposition of the covariance because this one is adapted to the Ising case where we're using that the spins have fixed size 1. We're instead using one where the mass varies, like a Pauli-Villas type cutoff, which preserves the structure that's ferromagnetic. Which is important, so we can again use the correlation inequality. We get a similar condition, but in this case, it requires getting good control over the susceptibility somehow when you see the ultraviolet divergences. But fortunately, that's something that can be done. The way we're doing is we're using these skeleton inequalities that are based on the random walk representation, which give a very simple way to get bounds on the 2-point correlation, higher correlation function as well, but we only need the 2-point function of these phi-4 models. Good upper and lower bounds, which are essentially what's given by perturbation theory. And one can use those to get see the countercurrents cancel and get sharp estimates in this ultraviolet regime on how the susceptibility blows up. And one needs to be a bit careful there to get somehow what one gets needs to be integrable after in a certain way. And so one needs to get the right bounds there. But it turns out it just works out exactly when these met. I mean, it's the same.
You're also just going up to the critical temperature or not?
Yeah.
Okay.
Yeah, it's the same. I mean, as soon as there's the bound on the
uniform volume and epsilon.
Yeah. I mean, as soon as you have, it only depends on the susceptibility.
Yeah, okay.
The susceptibility, if you have an upper bound on this, the remaining bound doesn't depend on epsilon L anymore. So it works up an infinite, up uniformly in the volume up to the critical point. If you define the critical point by finite susceptibility. Yeah, so that's pretty much it. I think I went over. time I had. And there's a few more pages I had prepared, but I knew that I wasn't going to get through all of them. But maybe let me finish here, and this seems a good point to stop.
No, that's very, very nice stuff. I mean, it's amazing how smoothly it comes out. I mean, this convolution trick is I guess that you use that with Thierry or what? Where you or does that just go back to Polchinski?
Yeah, I mean, so to get this Polchinski equation.
Yeah. Well, now this.
Also the Ising model, yeah, we've used that before, but somehow we couldn't. You mean to reduce the Ising model to the continuous model? Yeah. I mean, it's not very different from a Hubbard-Stratonovich.
Yeah, that's right. They get a continuous theory.
Yeah, it's almost the same, I think. I think what's
a little different because you're moving the temperature around.
Right. So I mean, if we do this just up to t equals 0, it's more or less the same as a Hubbard-Stratonovich. It's not exactly the same identity. I like this one a bit better, but probably one could use the Hubbard-Stratonovich there as well. But somehow this works out very smoothly. But then after at time 0, this has become continuous, and then we just use this Polchinski equation to.
Now I could do the same thing with XY or something like that.
Any model, as long as you can control this, any model is okay.
But so it's right there. The problem breaks down.
Yeah,
I mean you don't have that bound. In terms of susceptibility.
Right. So here, I mean, so we looked at when we did this for the Sine-Gordon model and the continuum. We didn't use this. We used the heat kernel decomposition, which is a better decomposition in principle, but it's not ferromagnetic. And we controlled this by expansion, basically, right? Kind of like a Meyer expansion. But here we, because there's this nice new correlation inequality, we reduced to, we use the specific cutoff, which preserves that the model is ferromagnetic, so we can use the correlation inequality. In some sense, I think so. Since you were asking why the exponent that comes out isn't optimal, I think if you could do all of this with a better so this decomposition where you vary the temperature is very natural, and it's very nice because it preserves all these nice properties, but it isn't the best in terms of localizing the scales, right? And if you do a better decomposition like the heat kernel, if we could do all of this with the heat kernel decomposition instead, and then the susceptibility would not be varying a temperature, but varying the cutoff of the heat kernel decomposition.
Yes.
I think we get the optimal exponent.
Then we wouldn't have this thing.
Exactly. The point is that we don't have the correlation inequality. So for the ultraviolet divergence, it doesn't matter so much because they're not as the ultraviolet divergences are easier than the infrared ones. So the cutoff, this one, I don't think it would improve much by using a better cutoff. But for these in the long distance, the sharp exponent, it's more sensitive. It's more delicate to get the exponent right. And we're losing, I think, because this covariance decomposition has fairly slow decay, and so I think there's probably a bit of overcounting of scales, which you wouldn't have with a sharper decomposition. But then we don't have the correlation inequality, and one would have to
work hard to get.
We'll have to work hard to.
That's non-trivial inequality.
No, the problem is it's
some inequality.
Yeah, it's non-trivial. It's kind of amazing.
There's a physical meaning. Maybe it means that if you put the background fields, then you have less correlation, right? Something like this.
Exactly.
Because the correlation is given by the kinetic.
Exactly. Intuitively, it's very natural.
It's very natural, right? Because it means that if you put some field, then let's say.
Yeah, but it's still remarkable in the sense that any field you can put. I mean, it's still.
Yeah, but still the correlation is only in the kinetic part, right? So really, if there is more on-site interaction,
It is natural, but
Yeah, but maybe it isn't even true for the XY or something.
yeah, I mean, for the XY model, it's not even true that the correlation matrix has positive entries because you have vectors, right?
Yeah.
We can't put it in, couldn't put it, so it's not even, so FKG isn't true, right? So it would be more delicate. I mean, it still seems conceivable that, but it certainly requires an idea how to use. I mean, for the XY model, I'm imagining that the matrix isn't positive or negative, but it's positive if you only look at the diagonal, and maybe you can control the off diagonal in terms of diagonal, but it's not near. I mean, one has to do something. It's not doesn't seem easy.
Any other questions or comments?
Yeah, I have a question. So you already mentioned this like paper of Haier and Schindler on the exponential ergodicity, for instance.
Whose paper?
Haier and Schindler.
Yes.
So they have like different ingredients that they use.
Maybe you can take your mask off.
Okay.
Feel you better.
Okay, so maybe this helps. So they have like different things that they use there, right? So I think they use the global bonds of Hendrik Weber. They use this kind of strong Feller property. I think they support their stuff like this. Is there like a dictionary between all of these things that they use and stuff that happens here?
I must admit, I don't really understand what they're doing. I mean, so yeah, now I remember. So they're using this support theorem for this SPD. Somehow that the SPD visits, you can probably explain better, visits somehow sufficiently much of the space where it's defined or something like that. And that seems to, and then there's some compactness argument, which I think the argument's also completely non-effective as far as I understand. It's a compactness argument. The spectral gap is not, can't be computed using the method.
So you
here it's complete, it's explicit. You can write it down.
You get stronger results than they can get with the SPD methods, right? Yeah,
I mean, we have a formula for it. I mean, the formula is not even complicated. So it seems a lot simpler what they do. Of course, we have this nice correlation inequality, which is
this came out of their work on the random field, right?
So I think they were interested in this. They wanted to show that the critical temperature doesn't increase if you add a random field. I mean, should they decrease, I think, and they just wanted to show that it doesn't increase, which is very natural. And they showed this by proving this inequality. But in my view, the inequality is more interesting than the result that it doesn't decrease. But I guess that's what motivated them, and they, as far as I understand.
Okay, it's beautiful work, Roland, as usual. So thanks very much.